Okay. Back to the beginning here. Don't pretend like you didn't see that. So I'm Brian. I'm from Docker. You can reach me as CPUGuy83 online, on Twitter and on IRC, or at brian.goff@docker.com. So today I wanted to talk to you a bit about what Docker is. How many people have, before today, heard about Docker? Pretty much everybody. How many have used Docker? Maybe a tenth of that. Great. So that's one of the questions I get a lot. People have heard about Docker, but don't really know what it is. So what is Docker? Docker is really fundamentally an answer to this. So this is an unfortunate reality of both developers and sysadmins. And actually, it's a really crappy reality that we're in with that. So we go, developer writes an application, hands it off to sysadmin, and 100% of the time, when we go to put it in production, this is what happens. And unfortunately, this creates a lot of animosity in between developers and sysadmins. Maybe sometimes, if the sysadmins are battle-hardened, they have come back to the developers and started to dictate how to write software to a person who writes software for a living, or vice versa, where I kind of, when I see this little girl, I kind of think like, oh, the developer did it on purpose to screw around with the sysadmins, and that's not a good situation either. So Docker lets you deploy anything. It doesn't matter if it's a SQL database or a Rails app or some network infrastructure inside. It doesn't matter. As long as it's a workload, it can run the workload. It runs on Linux servers. Doesn't matter if it's VMs or bare metal. It can run on any IaaS or VPS, and on virtually any distro. And I will kind of speak to some of the requirements of that later. And there has been some success on ARM, especially I think a lot of people have been working to get Docker running on Raspberry Pi, and obviously there was a Docker demo earlier on ARM, which was really awesome. So the basic idea of Docker is if it works on your laptop, it's going to work everywhere. You push it to staging, you push it to production, you push it to the cloud, you push it to some auto-scaling cluster, it's just going to work. It doesn't matter. But how does this work? Because this is kind of what we have to do on the sysadmin side. We have all these different applications and processes and services that we need to run, be it databases or front ends or what have you. And it's got to run across all these different platforms, servers, contributors' laptops, developers' laptops, staging, testing, you name it, any kind of hardware. I'm sure everybody knows that here. So we call this the Matrix from Hell. How many people have seen the Matrix from Hell stuff so far? One person, great. So it's new. So this is the Matrix from Hell. We have all these services to deploy across all these different mediums, and every single way requires a different way to deploy it. And as it turns out, there is another industry that has had the same exact problem, the shipping industry, where we need to ship, say, a sack of coffee beans or maybe some chemicals. And those are going to go on the same boat. And the dock workers have the responsibility of deciding what to put next to each other, how these things might interact with each other. And in addition to that, also to get the greatest density out of their shipping method. So maybe they're having a particularly bad day and they just kind of shove everything up as close to each other as they can, and you end up having interference between coffee beans and chemicals, and that would be super bad. So this is another matrix from hell. So we have all these different things to ship and all these different modes of transportation to ship it across. So the solution to this was a box. It was a really stupid, easy resolution. It was kind of like, I don't know, I remember when I was a kid, minivans had one sliding door. Then someone thought, second door. It was a pretty dumb idea to not have that second door. Likewise, putting it in a box just seems like the best idea because it provides this common interface that can work across any of these modes of transportation. The person that is packing that up can just put their goods in a box. The person who has to ship it doesn't have to worry about what's inside the box. They just have to stack the box up. And so, and I swear that was the only slide transition I'm going to do in there. So, turns out we can do that the same way with code. So Docker is a container system for code. So you write your Rails app, you put it in a box, you give it to your sysadmin to deploy it. And they stick it on their cluster with all their other boxes, and they don't have to know what's inside it. They just have that common interface, which is Docker. And there we go. The solution to the matrix from hell is just boxes everywhere. So to some, this kind of seems like a VM, and indeed there is some overlap. So here is the comparison of a VM to a Docker container. So here on the VM side, we have your server hardware, then you have your host OS, such as Linux or VMware, and then you have your hypervisor, such as Xen or KVM, and then even on top of that, you have each guest OS, which has its own things, such as Ubuntu or Red Hat, and then you have all your libraries and your binaries that support that operating system, and then on top of that, you have your actual application code. So, and ideally, each of these VMs, at least from the purple to orange side, are exactly the same. Like you generally don't want that to change. All that you really want to change is that top layer. So this is a lot of unnecessary duplication here. So what we do with containers and with Docker is we remove the hypervisor and share all resources across all containers through a common interface, which is Docker, which talks to the Linux kernel on the host OS. And then so we can, even in certain circumstances, and actually many circumstances, share the libraries across all these systems too, using copy and write file systems. And as it turns out, this changes the way you kind of think about doing software deployments and software development. Since you can share kernel resources, and since we have this awesome copy and write file system, you are able to package up your entire application environment and ship the environment and not bits of code. And we also get native performance because there's no hypervisor. So in a container, it's pretty much like a lightweight VM. And so it gets its own process space, its own network interface, its own everything you would expect out of a traditional operating system setup. But in addition to that, we share the kernel with the host. There is no device emulation or hardware virtualization or para-virtualization. And we limit root capabilities inside the container, which goes even further. So you can't do things like mount device nodes, mount file systems from outside the world, and pretty much just try to limit root access where needed. And so this produces super tiny images. So today you can go and you can take a VM and make an image out of it, and it's going to be probably tens of gigabytes. Or even something like Ubuntu. If you go to Ubuntu's website, you go to download the ISO, which is compressed. It's about 700 megabytes or so. On Docker, the Ubuntu image is about 250 megabytes. 250 megabytes for the full Ubuntu, which is pretty awesome because it doesn't need all the extra layers that are there to support things like network services and what have you, because that's all handled by the host. So I wanted to show a quick demo for that, which is a little bit difficult on multi-screen, but we will try anyway. There we go. So here we go. I have a set of demo setup. So we have this concept of a Docker file, where basically we're just telling it where to get an image from, then we're telling it to download some code, install NGINX, and then adding some static assets to it so we can run it. So I'm going to run this. So basically I'm telling it to build this image with this Docker file and run that demo. And if I could move this up, that would be great. So there we go. It went and it built all these various different copy and write layers for the image, and we have a container running. Now, hopefully, there we go. I'm in your container, and we can even do some fun stuff like edit anyway. So we're going to go rebuild it, and I got to shut off the other container. There we go, hello Lenaro. So you can see very quickly I was able to fire up a Ubuntu image with NGINX installed. And I can, so this is an image which should be something called web or something like that. So we have this web demo, and it's about 233 megabytes. And so I can actually package it up as a tarball and ship that across, or I can push that up to a central repository where another Docker daemon can also download it. And I will show you the central repository that Docker hosts later. All right, and we can even, so let's do something crazy. So there we go, I just booted up Ubuntu in about a quarter of a second. And I can do update. So you can see it's actually working, and well, I'm in the wrong scene. I'm sorry. I can see what I'm doing. You can't see what I'm doing. There, about a quarter of a second. And you can see, so it's a full-blown thing. It's got apt-get. It's got everything it needs to be an operating system and run things like NGINX and what have you. So Docker is a couple different parts. It is a Linux container engine. So Linux containers have been around for quite a while. If you used a Google service, you have used a Linux container, or at least a service inside of a Linux container. It is based on a couple of different Linux technologies inside the Linux kernel called namespaces and C groups to kind of provide that isolation and as well as resource management. So we have the engine here, which is just proper github.com/docker. There are lots of stars on GitHub and lots of contributors. Then we also have our ecosystem, which is kind of probably about 75% of what Docker really is. So we have a central repository called Docker Hub that has images that can be used by the community. So I can do things like Docker run CentOS, and I have a CentOS image. And many of these images are created by the actual project. So the CentOS people maintain the CentOS image for Docker. We can Docker run Redis, Docker run NGINX, or if you're feeling masochistic, Docker run WordPress. So there are over 30,000 Dockerized applications on Docker Hub, and it is really super easy to Dockerize an application. We saw a Dockerized NGINX where really you're just telling it to install NGINX and run some command. inside the container, which would be start NGINX. So Docker Hub is really pretty much GitHub, but for Docker. It's not a competitor to GitHub. It is specifically for collaborating on images for Docker. So you can push an image up, and somebody else can pull an image right off of Docker Hub. So when you build an image, I don't know if you saw on the output there, but it was saying something along the lines of run this command and then commit this to this ID number. So when each of these lines on the Docker file here is kind of like a git commit. It runs this command and commits it to a copy and write file system. So you can run, so the Ubuntu image is about 250 megabytes. You can run that, that same Ubuntu image 1,000 times on the same host, and you're still only using 250 megabytes because each container is pulling in that image and then putting a write layer on top of it. So they all share that same base image, and then they just, whatever they write is the size of the container. So boot to Docker is really awesome. It is a tool for developers, or even you can use it in production as well. It is an extremely minimal Linux distribution. It's about 27 megabytes. It boots really super fast, and we even have an installer so you can use it seamlessly on your development laptop in conjunction with VirtualBox. And by the way, it has a Docker file, so if you wanted to modify boot to Docker, you can very easily and very quickly. I've actually modified it to support the VirtualBox shared folders kernel modules. It just really quickly you add it in, and it just builds it out and builds out your ISO. It's really fast. Then we also have some awesome things on Docker Hub called automated builds, where you have on GitHub you have a project, you have a Docker file in it, and you tell Docker Hub when there's a commit or a push to GitHub, go ahead and go out and build this image for us. So it'll instantly be available on Docker Hub, which is really cool. And so we also have webhooks. So when an image is finished building, oftentimes there's there's things that you want to do, like maybe even just automatically deploy that new image. So what happens is on git push, you can tell Docker, so with an automated build, you would do git push. Docker Hub will pick that up, grab that repo, and build an image, and then that can send a hook back out to your services that you can use to do some crazy things like automatic deployment, testing, or Profit. So Docker is a tool. It's for developers who don't want to muddy up their laptop with a bunch of build dependencies, because you can run those. You can have those dependencies inside of a container. You write your applications and stick them in a box, and you give that box to your sysadmins, and they plug it in like Legos. And it's also a tool for change, to change the way you think about software deployment, the way you think about software development, so that instead of shipping bits of code that are going to work differently every time you go to run it on a different platform, you ship that whole environment in a box, so you don't have to worry about, is this going to work somewhere else? If it worked here, then it's going to work there because you've shipped the entire running environment and not just bits of code. So that we can take this and turn it into that. So that was my quick Docker intro. You can reach me here. If you're interested in Docker, we have 2 channels on Freenode, Number Docker and Docker Dev. Docker Dev is where all of our development conversations have, so all of Docker is developed in the open. So right now, Docker only works on 64-bit Linux. On x86 64-bit Linux and kernels 3.8 or higher, or if you're on Red Hat 2.6.32 or higher. And so there is the whole ARM thing. So there are some people that are working to get Docker running on Raspberry Pi. I think Michael was that gave the demo earlier with Docker on ARM. So there's a couple of different pieces there that need to happen for Docker to be for Docker to be a supported platform on ARM. There is both the getting it to work and to compile on ARM, and there's also the ecosystem. So the ecosystem I do Docker pull Ubuntu, and that's going to pull down currently 64-bit x86 code. And so the ecosystem needs to be set up in order to work in such a way that it can work on ARM or it can work on x86 64 at the same time. So there's some community involvement that needs to happen there in both of those arenas. So I will be happy to, I'm probably way over time, I'll be happy to answer questions afterwards, or you can hit me up online.
Or over lunch.
Yes.
Thank you, Brian. Thank you very much. And I don't know if it's a coincidence or if Brian had synchronized with Paul, but Brian used NGINX as one of the examples. And we have Paul and Rick from NGINX.
I was going to say the same thing, that it almost seemed like it was orchestrated, but that would require a lot of planning. Plug it in. I need an adapter. Thunder. This is. Oh, it's not the second one. Okay. Can you go ahead and get it to work?
Use the screen sharing thing.
Can you just do it? While we get the presentation up and running. Hello, can you hear me? Okay, so while we go ahead and get the presentation running, why don't I just go ahead and get started with what's available on ARM today, since that's probably what most of you are interested in. So our journey with ARM began when we began working with HP around the Moonshot system. So there's a version of NGINX that works for the M300 Avoton Intel-based system. And we also cross-compiled that for ARM. And we have a beta of NGINX running on top of ARM available today. If any of you are OEMs or ODMs and you want to get a copy of that, please find me and let me know. I'll be here all day, and we can get a copy of NGINX on ARM for you. So how many people here have heard of NGINX or use NGINX? Awesome, great, thank you. So for those of you who haven't, fundamentally at its core, what NGINX is a high-performance web server, static cache, and reverse proxy. NGINX has been around for quite a long time, even though as a commercial company we're relatively new. But development on NGINX started over 10 years ago. The original developer, based in Moscow, is Igor Sisoyev, who is the CTO of NGINX Incorporated. Initially, the goal of NGINX was to solve what we called 10 years ago the C10K problem, which is how do you connect as many as 10,000 connections to a single website. 10 years ago, that was a very big deal. Because, let's face it, there was a lot of dial-up, very slow dial-up connections that were out there. So that was a very big challenge that Igor was trying to solve when he developed the software. Well, fast forward 10 years, and the adoption of NGINX has grown by leaps and bounds. Just jumping down to the bottom, we are the #1 web server for the top 10,000 busiest websites. So there's a bit of a renaming going on. People aren't quite calling it the LAMP stack; they're calling it the LEMP stack, even though we're missing the E in NGINX. And overall, there are about 150 million websites, according to W3Techs, that is running NGINX. So we have about 20% of all active sites which are running NGINX, so we're quite prevalent in terms of web hosting and websites. There is a commercial company around NGINX that was created in 2011. We create commercial products, services, and support for NGINX, in addition to the open source product. And we are a venture-backed company, so we're a Series B VC-funded company. Some of our investors are NEA Capital, eVentures, and Michael Dell Capital. So basically, what do you do with NGINX, whether it's on ARM or any other processor architecture? What NGINX allows you to do is to build massively scalable websites. The reason why we do that versus some of our other competitors is that we use an event-driven architecture. So basically, you can have tens and hundreds of thousands of connections per server. So I referred to the C10K problem earlier and slow dial-up clients in 2002. Anyone who has a mobile phone in their pocket realizes that there's still a whole lot of slow clients that are out there. So one of the particular use cases of NGINX is it's very ideally suited to mobile application development. Mobile applications use very chatty protocols, and they always ping the server with using a RESTful API. So the demands for mobile development is very, very well suited to NGINX. Also, we use an event-driven architecture, and I'll have my colleague Rick Nelson talk a bit more about the architecture of NGINX, but we use an event-driven architecture that basically is non-blocking and asynchronous, very much like Node.js. So again, with other solutions, you quickly hit a wall in terms of scalability, memory, and CPU utilization. NGINX can scale 10x, 100x in terms of concurrency, but also with low latency. I think the best way to think about what NGINX does is it basically is a big shock absorber in terms of your web application or your website. It buffers, spoon feeds, and shapes HTTP application traffic, gives it security, and load balances across your backend servers. Another great thing in terms of the integration with ARM is that NGINX is directly tied into the Linux kernel and into the underlying CPU architecture, in this case ARM64. We're multi-core aware from the get-go. Anytime you improve the Linux kernel, anytime you improve the underlying CPU architecture, you get the linear type of performance scalability in terms of NGINX. Especially if you think about commercial load balancing solutions, those use custom ASICs, those use custom Linux distributions, and in many of those cases, you're not going to get the benefits of the great work that many people in this room are doing. Another benefit is that we don't have any kind of licensing or bandwidth restrictions in terms of ARM. So you can basically scale your NGINX instances as large or as small as you need them to be. We don't charge on a per core basis. We don't have any kind of licensing schemes that make it very difficult to get performance on top of the ARM architecture versus other architectures. And we do offer commercial support and services on top of NGINX. And I think one of the great opportunities for ARM right now for us is basically adapting NGINX in terms of what some of the custom silicon vendors are doing in terms of their own optimizations around the ARM server architecture. So with that introduction, let me go ahead and pass it on to Rick Nelson, who's our technical solutions architect, and he'll talk a bit more about the architecture of NGINX.
Hey, thanks, Paul. So I saw a lot of hands go up when he asked who used NGINX, so you may all know all this, so I'll be pretty brief on this. But again, NGINX is a web server, it's also a cache, it's also a reverse proxy. So it can do all those things in one package, all very high performance. So there are other tools out there that can maybe do all that, but not really high performance, and there are other products that can do high performance in one of their areas, but not all of that. So we're using all of that today. Again, the open source also does all this, where the commercial product is really focused on adding features is around the reverse proxy load balancing area and video streaming. Again, since a lot of hands go up, you may already be aware of the architecture of NGINX, but when Igor started, I mean, Apache was the web server out there, and you may know Apache back then was using a process for every connection. Those who understand how that stuff works, that's a pretty heavyweight way of handling connections, so really limited Apache. They moved on to a slightly better model, and that's a thread per connection. Still heavyweight, a lot of memory, a lot of CPU, a lot of context switching. So Apache is just really limited in how many connections it can handle. So Igor went with an event-driven model. So we have these meant, each one of those is meant to represent a worker process. So we run, the normal way is 1 per core. You can adjust that. But that's 1 process per core that's event-driven, asynchronous, so it can run thousands and thousands of connections. It's also been designed from the outset to be very lean. So if you watch a graph, and you can go online and find people who've done this, of Apache, as connections go up, its memory goes up. NGINX has a very, very low slope, very low ramp on that. So it's really lean and mean to doing that. And this kind of shows it in more detail. I'm not going to go through all this, but you can just kind of see these worker processes, and everything goes through that. We're also focused, NGINX does not do as much, for example, as Apache on the web server side or some other products. It's really geared toward static web content and proxy. And mostly HTTP, you'll see the fast CGI. So for dynamic content, we do that as a proxy. So we're not NGINX is not trying to be everything, but really focused on what it does really well, and then proxying to other servers. So if you're using PHP, for example, you can use FastCI to PHP FEM and have it do, because it's really good at serving PHP, and we're really good at proxying. So it's really geared, it's a little bit narrower on the web server side. But again, that architecture for all those connections turned out to be a really great reverse proxy, and that's why NGINX moved from not just being a web server to also being a reverse proxy.
Since I think Brian set the bar in terms of how much time we should be taking, I'm going to open this up to any questions that anyone might have about NGINX.
What's the largest configuration that you've tested with the? You were talking about the 10,000 connections. What's the largest that you guys have tested with, and it worked pretty good?
I'm not sure how big it's one we've tested with. Some of our customers have much bigger infrastructures than we would ever have in our lab. I mean, you can, for example, Netflix is doing all its streaming through NGINX, so they have obviously a much larger structure than we have. So we don't have actually like a lot of big labs.
Okay, I guess to rephrase the question, what's the largest configuration out there in regards to number of connections? Because you say 10,000. Is somebody doing 20,000, 100,000?
I mean, again, I don't have a lot of data on that. I would guess from my knowledge, it'd be in the hundreds of thousands, certainly.
Thank you.
So you mentioned that you did some work for Moonshot. What kinds of things was it? I presume that was the Atom initially. What kinds of adaptations did you need to do for the many node kind of system?
We haven't had to do a lot of work on our own. It's been a matter of waiting for the Linux to get ported. We don't require any special things in the Linux kernel. So if you give us a nice stable Linux, we'll run on that pretty much. So it's more a matter of testing and finding out other things. And we still have more testing to do, as you may have mentioned earlier. People are waiting to get. We've had some hands-on. We're waiting to get more consistent hands-on so we can do more extensive testing. So the actual port from our standpoint, again, we have done Atom in the lab as well as 32-bit, now 64-bit builds. But really, it's a matter of, it's really the underlying for us. We use things like OpenSSL, so it's all, we're really relying on those underlying pieces to be properly ported. So we know it functionally works, and we've done some performance testing and seen some good numbers. But we need some more hands-on in the lab before we'll have a really, a better picture of testing more scenarios.
So I was going to ask, is there anything which the hardware could do which would make your application perform much better than it does today? So my question is really to try and guide people that are doing silicon or for CPUs or networking, etc., if there are opportunities there for them to make NGINX as a web workload something which performs really well.
Yeah, Kiko, I think that's a great question. I think one of the opportunities that ARM affords is there is customization that can be done at the silicon layer. One of the things that we do a lot as a static content cache is we do gzip compression. So I know that some of the silicon vendors are focusing a solution on that part of the marketplace as well. We're at the point in terms of ARM development that we obviously want a common platform to develop to. But again, this is one of the things that we think. Rick brought up the issue of Netflix. I mean, Netflix does video streaming. Obviously, they're clogging up most of the internet around prime time with Netflix streaming. So anything we can do working with, Netflix is a customer of ours today, but anything we can do to optimize that overall solution architecture would be something we're interested in doing. So gzip compression was one of the things we've heard, and we'd love to hear some more cases where we can optimize around that kind of silicon solution.
Okay. Before lunch, we have one final session. We have been discussing about open source. So thank you. Thank you, Rick. Thank you, Paul. We have been discussing about open source and commercial spin-off out of open source. But there's a lot of open source and innovation that comes from the interactions with universities. So we have Jim Ballingal, who will introduce us opportunities for cooperations with universities. Thank you very much. You can use these or
Morning. That's interesting. Okay, well, thank you, Andrea. Sorry for the delay, everybody. It's really a pleasure to be here. So I'm with the Industry Academia Partnership. We are a collection of companies and the top universities in the world in computer science and electrical and computer engineering, those being MIT, Harvard, Carnegie Mellon, Cornell, Berkeley, and Stanford. This is an example of what we do. We're really focused on advancing cloud computing and what are the innovations required to meet the future goals. And in fact, our advisors articulated a specific set of goals. They're in a community white paper on our website. And those are to enhance the energy efficiency of cloud computing as well as handheld computing by three orders of magnitude in the next 7 or 8 years. Obviously, to reach that goal requires a lot of collaboration, a lot of innovation across the hardware and software value chain. So we get together at these workshops, talk about those, and pursue projects in common. This is up here, you can see Professor Christos Kazirakis from Stanford. I'm sure many of you know him. To his left are executives from Cisco, Brocade, and Cavium. Other members in alphabetical order would be Canonical. Kiko keynoted at our Cornell workshop a while back. Facebook, IBM, Imagination, LG, Rackspace, Samsung, SanDisk are the members. I invite you to consider membership. It's a great opportunity to work with students and professors. Next one is coming up at MIT in a week and a half. So this will have a very strong open source flavor to it. We have Professor Krieger, who's leading the recently announced Mass Open Cloud Initiative. A number of IAP members are participating in that as well as other companies. Matej Zaharia, I'm sure many of you know, the creator of Spark, is now a professor at MIT. He'll be speaking there. Kiko's threatening to show up again as well, and we'll have members from Rackspace and OpenStack and many other companies participating. So the Zen speaker talked about the gears of the cloud. Well, we have a set of gears here, and this is related to the open source movement. So the IAP is really a platform to engage not with academia only, but also with the open source contingent that's steadily growing on the academic campuses. And we see really a passion for students to participate in that and become committers. At the same time, we see, of course, the industry relying more heavily every day on OpenStack. So there's this complementary work here. Here's some of the OpenStack, open source groups we work with. OpenStack, notably Ubuntu, Apache Spark, Open Compute, Open Power, Mass Open Cloud, and that list is growing. But the question really, why Andrea invited me to really speak here today, is how can we kind of harness this energy, and to what extent, how can it help Linaro? So what we're doing now is building on these workshops. We deployed a training series for OpenStack on the campuses. We've conducted it now at both Berkeley and Stanford. We have one coming up at Carnegie Mellon next month, and this is a course that introduces students over a course of duration of 12 hours of training, 4 consecutive evenings, where they go through lectures and hand-on exercises through all the projects of OpenStack, Keystone, Glance, Nova, Neutron, etc. And the final exam, so to speak, is they actually have a physical cluster in the front of the classroom. They SSH into that over Wi-Fi and deploy a fully functional OpenStack cloud on that bare metal cluster. So that's the first step, and then we are proposing them projects of interest to specific IAP members for them to engage in and tie those into some of their class projects, their theses and capstone projects they can conduct over the next semester, summer, and fall semester. So it can take these projects we're parsing into units then being accomplished by an individual over a semester, a group over an individual, or either over the space of a year. Here's an example of some of the students participating in this. Some have no OpenStack experience, some have quite a bit of experience. Some have not committed, some have. But as I said earlier, we find a lot of passion for OpenStack in specific, as well as other open source solutions. And so we see us rolling this out, not just OpenStack, but to other open source solutions that are of interest to the members. So it's a way for members to look at holes in their OpenStack portfolio and get those filled in. The way the program works is my team sits down with the member that's interested in building out some of their OpenStack solutions. We understand what their projects are and then parse those into these buckets of duration and resource I talked about earlier. Match those up with professors and students that have an interest or resonate with those, go through the training phase, and then go into an implementation phase, code reviews on a monthly basis and so on. Other training exercises may be necessary to get around blockers that they're facing. Okay, so I'm at the 4-minute 23-second mark. Doing well. Okay, so the pop quiz is, what are 3 pipelines of value that would come out of this? Any ideas? Well, contributions, 1, correct? What else? Well, there's 3. I think it's pretty obvious. Most people get the first 2. It's funny, a lot of people missed the last one. The open source, you're also building the open source community. These are people who may never work at your company, but they may work in your ecosystem and will have as much value as some of your employees do. So that's what we're doing. Be happy to talk with any of you later more about the IAP if you'd like to get involved with it. Thanks very much for hosting us.
Thank you, Jim. Okay, we are perfectly on time. Lunch is outside at the atrium at the 1st floor, and we will reconvene at 2 in the breakout room that is here on the right, where we will have the key tech leaders available to talk about the demonstrations and any hands-on tests that you may want to try. Thank you.